Hi everybody. In this video we're going to take a look at the basics of limits. Limits form the foundation of calculus, and what we want to do now is really take a look at the nuts and bolts on how they work. So without too much further introduction, let's just dive right in. So I want you to take a second and consider this function for a minute. Maybe you want to graph it in any kind of graphing utility. We'll do that together later, but before we do that, I would love to take a second and find out the function value when x is 3. So that's one of the more basic things we've ever done with functions. Just want to plug in x equals 3. So without too much hassle, maybe some of you have already seen what's happening. What you get is, in your denominator, clearly you get 0. 9 plus 3 is 12. 12 minus 12 is also 0. So what we can determine very quickly is that the function is undefined when x is equal to 3. All right? That's all well and good. Not too much new here. But what we want to do is use this idea as a springboard. And we want to talk about over the next few minutes why even though the function is undefined when x is equal to 3, this here function actually has a limit as x approaches 3. And that limit is 7. And so by the end of this video, I would hope that you understand why the limit of this function as x approaches 3 is 7, even though the function is undefined at 3. So let's dive into that a little bit and figure out what's going on. So to do that, let's take a look at a really basic function, a really straightforward function. 3x minus 2 here is a linear function. I hope you can look at that and determine that with relative ease. The slope is, of course, 3. The y-intercept is, of course, -2. I just wrote -12. But it's -2. I almost did it again. So, fine. With that said, what we want to do is use this very basic function to determine what the limit is as x approaches, that arrow is red as approaches the value 2. So let's start with the end in sight. Let's start with the answer. To get the answer, take x as 2 and plug it in. 3 times 2 is 6. Minus 2 is clearly 4. So using this table of values, we know that the function value at x is equal to 2 is 4. So that's actually what the limit is. But that's not the most interesting part. That's not really what limits is all about. Limits, evaluating a limit is all about what's happening in these couple of boxes. So if you want to pause the video for just a second and evaluate those couple of boxes, I'm going to do that also. And here it is. So these are all of the function values when x is some kind of value. So as I said, fine, the function value itself is clearly 4. When x is equal to 2, y is equal to 4. The output is equal to 4. But what's really interesting is you can see that 4 happening from both directions. That is, as x is approaching 2, the y value is approaching 4. And that happens from both the left-hand side and it happens on the right-hand side. So more important than the actual function value here is the trend that's going on. And you can observe that trend not only with numbers, but you can observe that trend with a graph as well. So if we go ahead and graph the function 3x minus 2, as we'd already discussed, it's clearly a line. The slope is 3. You get a rise of 3, a run of 1, up 3 over 1, all that good stuff. And as we noticed earlier, when x is equal to 2, y is equal to 4. But what's really interesting about it is, in addition to seeing the table of values appear, you can drag along this line and witness as x approaches 2, y is approaching 4. And finally it gets there, it gets exactly to that point, x is equal to 2, y is equal to 4. And once again, the trend is more important than the precise point. Why is the trend more important than the precise point? Well, what that allows us to do is it allows us to plug in gaps in holes or in functions. So sometimes there's a hole in a function, sometimes there's a gap in a function. And in this one, for instance, in a limit, evaluating the limit, looking at that trend is actually going to be what allows us to do that. So let's do that. All right, so first things first, the definition of a limit, you can pause this video to write it down. But basically the limit means when the function value gets close to an output L as the input x approaches some value c. So you can go back and to the previous one and relate f of x, c, and L to specific numbers. With that said, let's look at the next one. So let's return back to that. Let's return back to that function that we started the video with. And what we remember is that when x is equal to 3, this function is undefined. So it's not quite as easy to see the limit when you can't evaluate it right here. So what we have to rely on is we have to rely on what's happening around this value, this c value by the definition. So take a second, see if you can fill in this table of values before I do. I'm going to pause the video and fill them in also. I'm back now. So what I hope you have done is to take a look at the trend on both sides of x equals 3, as I did here. And do you see a trend? Is the output value approaching some value that can be seen from both sides? Is it approaching one value from the right? Is it approaching a value from the left? It seems to be approaching 7 to me. So what we're going to do is we're going to verify that in just a second via a graph. But basically what happens is the limit as x approaches 3 of this function x squared plus x minus 12 over x minus 3. As we said in the very beginning of this video, the limit as x approaches 3 of this function is 7. And numerically, we can see that trend on both sides of 3. And then we're going to take a quick look at the graph to verify that. And so here is here's the value x equals 3. What's happening on the graph around that? First things first, the function is actually undefined. Let me see if I can get that to stick. The function is actually undefined when x equals 3. But what's happening around it? As you get closer and closer to x equals 3, what's happening to y? What's happening to the output? It's getting closer and closer to 7. Never quite reaches it because it is undefined there. But because the trend matches on both sides, we can conclude that the function, or the limit as x approaches 3, is in fact 7. So we can count on that. And then one quick note, don't let this keep you down for too long. The fact that the function is undefined when x is equal to 3 has no bearing on whether or not the limit exists. And that'll make a little more sense when we get to video number 3 in this sequence about when limits exist and when limits fail to exist. But just because a function is undefined at a particular location has no bearing on whether the limit exists or not.